Welcome to AudioCert, where the official study guides are brought to life. Today we're embarking on a deep dive into the EC Council Computer Hacking Forensic Investigator, or CHFI, certification. Now, this isn't just about, passing an exam. It's really about equipping you with the vital skills to become a digital detective. You'll learn how to identify, collect, preserve, and meticulously analyze digital evidence. Think of it as your essential toolkit for fighting cybercrime and ensuring justice in our increasingly digital world. Our mission today is a focused exploration of Chapter 6, Windows and Linux Forensics. Now, you might be thinking, why a whole chapter dedicated to both operating systems? Well, in the real world of digital investigations, you rarely get to choose your preferred environment. You'll inevitably encounter a mix of Windows and Linux systems. So our goal today is to make you conversant with both, understanding their unique strength and, well, their subtle weaknesses so you can combine their tool sets effectively. Imagine using Windows for its ability to capture fleeting live data, then turning to the powerful, deep analytical capabilities of Linux. It's really about having the best of both worlds at your fingertips.
Exactly. Our ultimate goal for this deep dive is to guide you through the intricate processes and powerful tools available for forensic analysis on both Windows and Linux hosts. We're going to explore precisely where to find evidence, the critical methods for collecting it in a forensically sound manner that's paramount for integrity, you see, and what powerful tools are at your disposal to interpret that evidence. Consider this your essential training, building a robust toolkit for navigating the complexities of digital evidence across the most common computing environments you'll encounter. It's about being truly prepared for, well, pretty much any scenario.
It's true. Even for those of us who might, lean towards Linux, you will absolutely, inevitably face a live Windows system. And here's a crucial insight. A vast amount of highly volatile evidence can be collected before you ever think about shutting that system down. Why is this so important for you? Well, because powering down a system, while sometimes necessary, often means that valuable, time-sensitive information is lost forever. Think of it like a conversation happening in a room. If you just flip the light switch off, all that interaction vanishes. Volatile data is kind of like that conversation.
That's a perfect analogy. Beyond just finding obvious files on a hard drive, the true art of evidence location on Windows lies in uncovering data of forensic and legal importance, something absolutely crucial for both criminal investigations and civil cases. Windows, given its widespread use, is truly a treasure trove of evidence, and that evidence can often be found even in its most hidden corners. We're talking about more than just your typical documents here.
Okay, so where are these crucial sources of electronic evidence commonly found on a Windows host?
Well, of course, there are the files themselves, your documents, executables, images, but even these can be manipulated, so you'll always be paying close attention to things like file attributes and timestamps, which can tell a hidden story. Then we have slack space, which we'll delve into a bit more later, but it's essentially leftover storage on the disk, kind of like the space between words on a page, almost. The swap file, also known as Pagefile.ss, is critical as it acts as an overflow for system memory.
Right, like virtual memory on disk.
Exactly. Unallocated clusters contain data that was once part of a file but has since been deleted, meaning the space is marked as available, but the raw data often still resides there waiting to be found. And quite often, you might uncover evidence hidden in unused and hidden partitions that attackers cunningly create to stash their malicious tools or stolen data, hoping no one looks there. It's like finding a secret compartment in a desk drawer.
Right. And when you're sifting through all these potential locations, it's absolutely vital to remember a critical order of operations. It's less of a suggestion and more of a forensic checklist to ensure nothing is missed. You gather volatile data first, because it's the most fragile and disappears quickest. Then you move to things like internet traces and then everything else in between. This systematic approach ensures you're preserving the most fleeting evidence before moving on to more persistent data. It's about securing the most fragile clues first, every single time.
Okay, let's zoom in on this concept of gathering volatile evidence because it's paramount, yet, like you said, often overlooked. Volatile data is, quite simply, any system information that disappears the moment the power goes off. We're talking about things like data in the CPU's registers, information in the cache, the contents of physical memory, your RAM or random access memory, active network connections, and the list of currently running processes. Why you need to know this inside and out is because this data provides a real-time snapshot of the system's current state. It reveals what was happening at that exact moment of the incident.
If you just pull the plug, that critical snapshot is gone forever, often irreplaceable.
That's the challenge, isn't it? This raises an important question. How do we collect this incredibly delicate and time-sensitive information systematically and reliably without causing further damage? The answer often lies in adhering to established best practices, particularly RFC 3227, titled Guidelines for Evidence Collection and Archiving. This document, which you can find at www.fact2.org, rfc-srfc3227.html, provides a crucial priority roadmap known as the Order of Volatility.
RFC 32227, got it. So this order of volatility is like a checklist.
It's more than just a checklist. It's a critical sequence you must follow to avoid destroying evidence. At the very top, the most volatile, are registers and cache, which hold data actively being processed by the CPU. Super fleeting. Next come dynamic network and system state information like the routing table, the address resolution protocol, or ARP cache, the process table, and kernel statistics. Following that, we have memory, or RAM, then temporary file systems. Only after these highly volatile sources are secured do we move to more persistent data, like the disk. Further down the list, we consider remote logging and monitoring data, then the physical configuration and network topology, and finally archival media, which is the most stable, like backups.
That makes sense, like securing a crime scene.
Exactly. Imagine a crime scene. You secure the most fragile evidence first, like maybe footprints in mud, then move to more stable clues. Vulnerable data is like that mud print, or maybe even the smoke still hanging in the air. The physical disk is more like the building's foundation.
Considering the vast majority of systems worldwide run Windows, it's a statistical certainty that a significant portion of cyber incidents, and thus your forensic analyses, will involve Windows hosts. This means the ability to gather data from a live Windows system isn't just valuable, it's often unique and irreplaceable. While offline imaging and meticulously searching through disk images are standard for any forensic analyst, the volatile information from a live system can tell a story that offline analysis simply can't. There are numerous scenarios where live analysis isn't just beneficial, but absolutely essential. Imagine a critical e-commerce platform like eBay or Amazon, where every minute of downtime costs millions.
Or critical infrastructure.
Exactly. Infrastructure systems, like a power grid, where an outage could have catastrophic consequences. Even in medical devices, taking a system offline might not be an option. In these situations, the ability to capture and analyze a system while it's still running is incredibly valuable. These specialized tools don't just capture static images, they capture and analyze critical volatile data that would simply vanish if the system were shut down. In fact, they can often help you quickly determine if an incident truly occurred, confirm its nature, and gather immediate intelligence.
That's precisely why tools like Helix are so groundbreaking. What's fascinating here is how Helix tackles the fundamental dilemma of live forensics. Any action you take on a live system, even just running an application, alters its state. Yet powering it down destroys volatile evidence. Helix is specifically designed to navigate this. It acts as a portable forensic environment, typically run from a CD-ROM or USB drive, providing forensically sound access to many Windows-based tools without unnecessarily altering the target system.
So it's like a self-contained toolkit you bring to the system.
Pretty much. A key benefit of Helix.exe is its ability to operate as a standard application across a broad range of Windows versions, from 98 SE all the way to Vista. It provides a graphical user interface, a GUI for an incident response screen, and integrates a Windows command line interface, giving you a powerful, unified control panel. But here's where its forensic integrity truly shines. Helix maintains known safe versions of built-in Windows tools, like netstat for network statistics or ipconfig for Internet Protocol configuration.
Ah, so it doesn't rely on the potentially compromised tools on the system itself.
Exactly. This crucial feature prevents attackers from replacing legitimate system tools with malicious, Trojanized versions to hide their tracks. By using Helix's trusted versions, you preserve the integrity of your evidence, ensuring the information you collect hasn't been tampered with at the source. It's a vital safeguard in any potentially compromised environment.
That's such a critical point about maintaining integrity when the system itself might be compromised. So when you're working with Helix.exe, what kind of powerful tools are you gaining access to?
It's quite a comprehensive set, really.
You'll find utilities like .cap extractors for compressed files, essential network command line tools like ipconfig and netstat, and even process management commands like kill. Beyond these, Helix provides a robust file attribute browser, the highly regarded rootkit revealer from sysinternals, which is excellent for finding hidden malware, a screen capture application for visual evidence, and even the PC Inspector data recovery tool. The power here lies not just in capturing disk images, but also in directing those images to remote analysis systems, which can be incredibly useful in a real-world investigation.
But remember that crucial warning about RAM.
Right. The Helix warning.
Yes, Helix is designed to capture physical memory, or RAM. Always capture RAM first, before any other actions or running subsequent tools, as those actions will inevitably alter memory and could destroy critical, time-sensitive evidence. Get the memory dump before you do anything else.
Okay, RAM first. Got it. Now, you mentioned Helix contains a lot of tools. Can we break down some of the specific categories?
Absolutely. To go deeper into the specific capabilities you'd find within a forensic environment like Helix, let's highlight some categories. For password recovery, you've got tools like Access PassView for Microsoft Access database files, MDB files. Asterisk Logger reveals passwords hidden behind those asterisks in text boxes.
Oh, that's handy.
It is. Then there's Mail PassView for various email clients like Outlook, IncrediMail, Eudora. MessenPass for popular instant messenger programs, MSN, Yahoo, ICQ, AM, Trillion, that sort of thing. And Protected Storage PassView gets those Internet Explorer and Outlook Express passwords stored when you clicked Remember Password. The key insight here is how many places credentials can pop up, which really underscores the need for good password practices and for investigators knowing where to look.
Definitely highlights the vulnerabilities. What about system and disk analysis?
Right, for general system and disk analysis, you'd find utilities like Drive Manager to identify drive types, volume labels, vendor info, and crucially, serial numbers, the unique IDs. FAU, that's Forensic Acquisition Utilities, is for imaging system memory and attached devices. And FTK Imager Forensic Toolkit Imager is a very robust tool. It acquires physical device images, lets you view data from tons of file systems like FAT, NTFS, EXE23, HFS, HFS plus HBCDFS, DVD, and it can create multiple image formats like DD, SMART, and ENCASE images.
FTK Imager is a big one. And internet activity.
Yep. For internet activity, tools like Aletta and Pasco parse cookie file information and index.file info into formats you can easily pull into a spreadsheet. IE-Cookies View and iHistory View are specifically for digging into Internet Explorer cookie details and visit website history. These tools can quickly reveal the user's web footprint, which is often central to an investigation. You can see what they viewed, delete cookies, save them, even view cookies from other users or computers sometimes.
Wow, okay. And for system monitoring and integrity.
Yeah. Then you have powerful system monitoring and integrity tools. Process Explorer is fantastic for showing active processes. Accounts own them, handles, DLLs, dynamic link libraries, and memory-mapped files. It has a great search function, too. Rootkit Revealer, as mentioned from CIS internals, is crucial for detecting those stealthy rootkit hiding mechanisms by listing discrepancies between the registry and file system APIs. And for ensuring evidence integrity, which we keep coming back to, Secverif collects security info and creates XML-based reports with MD5 hashes. Windows Forensic Tool Chest, or WFT, automates a lot of incident response tasks, collects relevant security info, produces HTML reports, logs extensively, and provides those vital MD5 checksums for verifiable output.
It's not just the individual tools, it's the sheer breadth of capability that a suite like Helix brings.
Exactly. It allows you to quickly uncover various types of evidence, from hidden credentials to system tampering, all from one controlled environment.
That's a powerful arsenal. But knowing these tools exist is one thing. Understanding how to actually deploy them in a real-world scenario is another. Let's walk through the basic steps of using Helix Live for Windows.
Sure, it's designed to be pretty user-friendly.
First, you'll start Helix Live for Windows, typically by its auto-run feature from a CD, or by double-clicking helix.exe. You'll then be presented with the Terms of Use, which you'll need to accept to proceed, similar to what you'd see in Figure 6.3 of your study guide. Once you agree, the main Helix screen appears, as shown in Figure 6.4. A unique aspect of Helix is how it manages its interface. It doesn't appear in your standard taskbar. Instead, it places a small icon in the system tray, as shown in Figure 6.5, which you'll use to access the program.
Right. You double-click or right-click that tray icon.
Exactly. Double-clicking or right-clicking that icon and selecting Restore will bring the main Helix window back to the foreground. From the main screen, you'll find 3 core examination options. Preview system information, acquire a live image using DD, that's data duplicator, and incident response tools for Windows systems. If you select the incident response tools icon, a small triangle appears, as in Figure 6.6. Clicking on that triangle then reveals access to even more tool pages.
And that's where you find things like reference docs.
Yep, reference documents in PDF format, a CD-ROM host OS browser that shows file details like name, dates, attributes, CRC, cyclic redundancy check, MD5, and size, a picture scanner, and a place for investigative notes. It's important to remember, though, that when examining a live system, your actions can modify it. For example, simply accessing a file can change its access date. Helix cannot entirely prevent this in live mode, but being aware of it is crucial. Helix also offers a quick launch feature, which, as shown in Figure 6.7, provides fast access to additional powerful tools, ensuring you have a comprehensive set of options throughout your investigation.
If we connect this to the bigger picture, once you've collected data, whether it's a full disk image or just specific files, MD5 generators become absolutely critical. They're essential for maintaining the chain of custody and ensuring evidence admissibility in any legal setting. These utilities create a cryptographic hash, which is basically a unique, practically unreplicable digital signature of a piece of data.
Like a digital fingerprint.
Exactly like a digital fingerprint. Here's the power. If you run the utility on a file when you first acquire it, get that hash value, and then run it again later, maybe right before presenting it in court, and you get the exact same hash value, well, you have verifiable proof that the data has not been altered. It's an indispensable layer of protection in digital forensics. Tools like Chaos MD5, Secure Hash Signature Generator, which supports MD5, SHA-1, Secure Hash Algorithm 1, and CRC MAT MD5 and MD5 Checksum Verifier all perform this vital function.
That cryptographic integrity is absolutely non-negotiable. Now, even with the prevalence of graphical user interfaces, GUIs, command line tools, remain absolutely indispensable in digital forensics. They offer precision, speed, and often capabilities that GUI tools simply don't. Let's look at a few powerhouses you should definitely know.
Agreed. The command line is often faster and more direct for specific tasks.
First up, Pslist. Part of the incredibly useful SOS internal suite list is a fantastic tool for quickly assessing what's running on a system. It displays detailed process, CPU, and memory information, and even thread statistics for all processes. It shows you things like execution time, kernel and user mode time, and physical memory assigned. While its full syntax can look complex, for most forensic purposes, you'll want to remember key parameters like NES-M for memory-oriented information and MES-T to display a process tree showing parent-child relationships.
That process tree can be really revealing for malware analysis.
Definitely. These are your quick go-tos for understanding resource drain or the relationships between processes, which can be critical for identifying malicious activity. Then there's Fport, that's Fileport, a Foundstone tool. This utility takes NetStat to another level by mapping all open TCP/IP, Transmission Control Protocol, Internet Protocol, and UDP, User Datagram Protocol, ports directly to their owning applications. This includes the process ID, PID, the process name, and its full path. It's incredibly useful for quickly identifying unknown open ports and the potentially suspicious applications that might be listening on them.
So you can see exactly what program is using what port.
Exactly. You can use simple switches like P to sort by port or A to sort by application, making it easier to pinpoint anomalies. Finally, Psloggedon, another gem from the SUSTOL suite. This tool displays both locally logged on users and users who are logged on via network resource sharing for either the local or a remote computer. It does this by examining specific keys under HKeysers in the registry and utilizing the NetSessioninum API, that's Application Programming Interface. For most investigations, the IL parameter is incredibly useful, as it will show only local logons, helping you focus on direct user activity on the machine.
These command line tools, while they might require a bit of familiarity, really give you surgical precision in your investigations, allowing you to uncover details that might be hidden from simpler GUI views.
Absolutely. Now, you mentioned FileSlack earlier. This raises an important question. What exactly is FileSlack, and why is it so significant in digital forensics?
Right. So a Windows disk cluster is a fixed-length block of data used to store files. Think of it like a container of a set size. Because a file's size rarely perfectly matches the size of one or more clusters, there's almost always leftover space at the end of the last cluster used by that file. FileSlack is precisely this area, the space on a Windows disk between the actual end of a file's data and the end of its last allocated cluster.
Okay, so it's the unused bit at the end of the container.
Pretty much. And this space isn't empty. It's often filled with data from the system's memory, whatever was in RAM at the time. We call this specific part RAM slack. The reason it matters so much is that this seemingly innocuous space can be a goldmine of evidence. Usernames, passwords, sensitive information, even fragments or entire files from previous operations can be found here.
Stuff the user thought was gone.
Often, yes. Attackers and even regular users often overlook this, making it a vital source of evidence. And here's a key point. The larger the cluster size configured on a drive, the more file slack you're likely to find, and thus potentially more forensic data. Tools like NK software are specifically designed to help forensic investigators conduct complex investigations involving file slack and unallocated space, allowing them to precisely recover these hidden fragments and piece together a more complete picture of system activity.
Absolutely. Finding those hidden gems in file slack can make or break a case. Moving to another indispensable component, examining the file system itself. This allows you to reconstruct events and truly understand what happened on the machine. Simple commands, for instance, like dir-od, which sorts files in a directory by date, can play a hugely significant role. This one command alone can help an investigator ascertain the operating system's installation date, the timing of service packs and patches, or when critical drivers were updated.
Building that timeline.
Exactly. The key takeaway for you here is to always focus on files that have been updated most recently, as they're often the most relevant to recent suspect activity, helping you build a clear timeline of events. And when it comes to checking the integrity of a system, particularly its drivers, a very useful built-in tool is Sigverif.exe. This tool verifies digitally signed drivers, and finding unsigned drivers can be a significant red flag for malware or system compromise. It's a quick, easy way to spot potential foul play.
How do you run that?
It's simple. You just go to Start Run, type Sigverif, and click OK. From there, click the Advanced button, select Look for other files that are not digitally signed, and then point it to the WNT System32 drivers folder, then click OK. After Sigverif.exe completes its check, it will display a list of all unsigned drivers, and the full results are conveniently saved in Sigverif.txt in your Windows folder, marking any unsigned drivers for your review. It's a great first step in a system health check.
Complementing tools like Sigverif for deeper textual analysis is the Word Extractor forensic tool. This application is designed to extract human-understandable interpretations from binary computer formats. It's quite similar to the unix strings command, which many Linux users are familiar with.
Right, strings is super useful.
It is. What Word Extractor does is replace non-human words or unreadable binary sequences with spaces or dots, effectively making hidden text visible. This is incredibly useful for quickly sifting through large binary files, like memory dumps or disk images, to find keywords, email addresses, or other textual evidence that might otherwise be buried and invisible without specialized tools. It can multitask, supports drag and drop, and sees results in TXT or RTE formats without altering your system's registry or DLLs. What's fascinating here is that the Windows registry is truly the heart of the operating system's configuration. As such, it stores a wealth of forensic data about running services, logged-on users, and system history. Interpreting this data is absolutely essential for any investigation. For the exam, and indeed for real-world scenarios, you need to be intimately familiar with several crucial registry keys. These keys often reveal programs configured for persistence, meaning they launch automatically when the system starts or a user logs in, making them prime locations for malware.
The usual suspects for autoruns.
Exactly. Specifically, under HK Local Machines software Microsoft Windows current version, you'll want to check the Run Once, Run on X, Run Services, and Run Services on keys. These are classic places for attackers to ensure their malicious code executes every time. Also critical is HK Local Machine software Microsoft Windows NT current version WinLogon, which controls the entire Windows logon process. Beyond HK Local Machine, always remember to check these same types of keys under HK Currentisr and HKeezer's default, as user-specific settings can also reveal important clues about an attacker's activity or a user's behavior.
Right, the registry is a goldmine, but navigating Registry 32, the built-in registry editor, can be cumbersome, especially when you need to perform mass searches. It simply lacks that functionality to find and display all instances of a given string.
Yeah, searching in Regin is painful.
It really is. That's where a tool like RegScanner from Nearsoft comes in. It fills this gap brilliantly, allowing you to scan the registry for any string and display all available instances in a single consolidated view. From that view, you can easily jump to a specific key for further examination or export the results to a RE file or even HTML. It's quite versatile, even supporting searches for Unicode strings within binary values. It's a powerful enhancement for any Windows forensic toolkit, turning a tedious manual search into a quick, automated process.
This raises an important question. Beyond simple login names, how are users and security contexts uniquely identified in Windows? This is where Microsoft Security IDs or SIDs come into play. These are unique, immutable identifiers for users, groups, and computer accounts. You can find them in the Windows Registry key, HK Local Machine software, Microsoft Windows NT current version profile list.
Okay, profile list.
Yep. Each SID within this profile list key is associated with a specific username, providing a direct link between a numeric ID and a human-readable account. Other related IDs that are critical to system operations and security and often contain valuable forensic insights include those related to encrypted file system information, event logging, and utilities to retrieve and steer media access control addresses. Understanding these identifiers and how they're stored is key to piecing together a user's activity and system configuration.
Switching topics slightly.
Right.
When Windows inevitably crashes, it often creates a memory dump file, which holds incredibly vital diagnostic information. Why is this important for you? Because it can contain a snapshot of what was happening in the system's memory at the exact moment of failure.
The blue screen of death dump file.
Exactly. Which is crucial for diagnosing system bugs and understanding program failures. To ensure a memory dump can actually be produced, the system requires a paging file of at least 2 MB on the boot volume. Without it, even a large paging file elsewhere won't suffice. These dumps contain raw binary, octal, or hexadecimal information, which, while complex, can reveal a wealth of information about system state.
Where do you find these dumps usually?
Microsoft provides a tool called dumpcheck.exe specifically to check these memory dump files for information. Typically, you'll find these small memory dump files in the system root mini dump folder. What kind of information is contained in a memory dump? It generally includes the stop message and its parameters, a list of all loaded drivers, the processor's context, PRCB, kernel context, eProcesses for stopped processes, thread context, eThread, for the thread that stopped the system, and the kernel mode call stack for that thread. For example, Windows XP Professional often uses its paging file, pagefile.ss, to create these memory dumps. And for offline analysis of any process's memory contents, there's a tool called PMDump, that's postmortem dump, which dumps the memory of a running process to a file for later examination.
Ah, so you can dump a specific process's memory, not just the whole system after a crash.
Exactly. PMDump lets you target a specific running process, which is great for analyzing potentially malicious software without waiting for a crash.
This raises an important question. What exactly is virtual memory, and how does it relate to forensics?
Good question.
Virtual memory is an ingenious way the operating system expands the perceived available RAM, random access memory, by temporarily using slower hard drive space. It's essentially an imaginary memory location. Programs use these virtual addresses for data and instructions that aren't immediately needed or don't need to be accessed as frequently. When these virtual memory locations are called upon, the operating system copies them into physical RAM. This process of copying virtual pages from disk to main memory is known as paging or swapping. So in a forensic context, the pagefile.ss can contain snippets of information that were once in RAM, including sensitive data, even if the primary memory has been cleared.
So even after RAM is gone, traces can remain in the page file.
Precisely. It's like finding old notes scribbled in the margins of a book. They might not be part of the main story anymore, but they can offer valuable context or clues.
And for even deeper real-time insights into your system's memory, particularly for process analysis, there's a tool called System Scanner. It's available from www.codeproject.com/w2ksystemscanner.asp. It's designed as a more powerful replacement for the built-in Windows Task Manager. While Task Manager gives you a basic overview, System Scanner provides much more specific process information.
Like what kind of info?
Things like the IDs of all threads within a process, handles to DLLs, and crucially, a visual map of a process's virtual memory, as shown in Figure 6.9 in your study guide. This level of detail is invaluable when you're trying to understand what malicious software might be doing or how a legitimate application is truly behaving under the hood. It allows you to suspend threads, view specific memory regions, and even terminate processes directly.
If we connect this to the bigger picture, when you need a truly comprehensive and advanced work environment for digital forensics on Windows, Xway's Forensics is an incredibly powerful solution. It's based on the hex editor WinHex, and it offers a vast array of features.
Xways is another big name in the field.
It really is. Key among its features are forensically sound disk cloning and imaging, essential for preserving evidence. It can interpret complex directory structures even within raw image files, and offers native support for a wide variety of file systems: FFT, NTFS, XT234, CDFS, UDF, HFS, RiserFS, and UFS. This broad compatibility means it can handle almost any drive you encounter. Beyond basic imaging, Xways includes built-in interpretation of RAID 0 and RAID 5 arrays and dynamic disks. It can view and dump both physical RAM and the virtual memory of running processes, a goldmine of volatile data. For data recovery, it offers various file carving techniques and boasts a robust file header signature database using GRT notation to identify file types regardless of their extension.
So it can find files even if their names or extensions are wrong.
It's adept at gathering slack space, free space, and even interpartition space, helping uncover hidden data. It can perform mass hash calculations, CRC32, MD5, SHA1, SHA256, for integrity verification, and has seamless viewers for over 400 file types, including excellent support for email examination. Furthermore, it automatically identifies encrypted MS Office and PDF documents, finds embedded pictures, includes an internal viewer for Windows registry files and event logs with automated reporting, and offers extensive logical search capabilities for fragmented data, compressed files, and various text encodings.
Wow, that's a lot.
It even includes features like skin color detection for specialized cases, write protection, case management with audit logs, and comment association for reports. In essence, Xway's Forensics provides an incredibly deep and integrated environment for the serious forensic investigator, covering acquisition, analysis, and reporting with exceptional detail and integrity.
So what does this all mean for tracing user activity, particularly online? The fact is, web browser activity leaves a surprisingly clear digital footprint, and knowing where to look is half the battle. When investigating internet traces on a Windows system, especially for Internet Explorer, there are several key locations to investigate.
Where should we look first?
First, cookies. These are small text files websites store on a user's computer, often found at C. Documents and settings, %your name %, cookies in newer Windows versions like XP or C, Windows cookies in older ones like 98ME. These can contain session IDs, user preferences, tracking data, all sorts of things. Next, the history folder stores records of visited sites, a clear trail of navigation. The typed URLs, those uniform resource locators you manually type into the browser, are usually stored within the history index file itself. And finally, temporary internet files found in the temp folder contain cached images, web pages, and other media. These files can hold valuable information about user activities, including content from visited websites, even if the user attempted to clear their history.
To help with this, there are specific tools designed to delve into these internet traces. Traces Viewer, for example, allows you to view all cached images, Flash movies, and web pages stored by Internet Explorer. While it might offer a function to remove traces, it's important for an investigator to remember that evidence may still be recoverable from the underlying disk, even if the tool claims to remove it.
Good point. Deletion isn't always deletion.
Exactly. Then there's IE Cookies View, a utility that displays detailed information about all cookies stored by Internet Explorer. It can sort, search by website name, copy information, and even view remote cookies if you have the necessary permissions. Similarly, IE History Viewer parses the history files, listing all visited URLs, and allowing you to export that list to text HTML XML. These tools quickly piece together a user's online actions, revealing critical timelines and access content.
Another critical area for forensic analysis, and one often leveraged in disaster recovery scenarios, is the system state backup. A system state backup is, in effect, a complete snapshot of the entire system. It copies everything essential to functioning, so that in the event of a system crash, driver corruption, or critical file failure, you have a comprehensive restoration point. It's crucial to understand that simply backing up the registry isn't enough for a thorough forensic analysis or complete system recovery. An extensive full system state backup is essential to truly secure a system against malfunctions.
So what exactly does a full system state backup save?
Good question. It includes the Active Directory, NTDS, vital for network authentication in Windows domains, the Windows boot files necessary for the OS to start, the common plus component object model plus class registration database, the entire registry, the system volume, SYSVOL, which stores server copies of domain public files, and the IS Internet Information Services metabase for web servers. The process to create one is fairly straightforward through the Windows Backup utility. You basically start the backup wizard, choose to back up the system state, select your destination, and schedule it. This comprehensive safety net ensures that not only can a system be recovered, but a full forensic snapshot is available if needed.
Now let's shift gears to something truly intriguing: how attackers sometimes hide data in plain sight. What's fascinating here is a relatively unheard of compatibility feature of NTFS' new technology file system called Alternate Data Streams, or ADS.
ADS, I've heard of that. Used for hiding stuff, right?
Precisely. This feature, originally designed for compatibility with Macintosh files that historically stored metadata in separate forks, has unfortunately become a clever method for attackers to hide rootkits or hacker tools on a compromised system. This allows them to execute malicious code without being easily detected by system administrators. Alternate data streams are strictly an NTFS feature and can effectively be used as a stealthy method of hiding executables or proprietary content within another, seemingly innocuous file.
How easy is it to create them?
That's the alarming part. It's simple. Common DOS disk operating system commands, like type, can be used in conjunction with a redirect symbol and a colon to fork one file into another. For example, the command type C malicious.exe, WinSystem32calci.malicious.exe will take a malicious executable and attach it as an alternate data stream to the legitimate calc.exe Windows calculator program.
And calc.exe still works normally.
Yes, calc.exe will appear to function normally, but the malicious code is hidden within it. The significant detection challenge is that files within ADS are almost impossible to detect using native file browsing techniques, such as the command line or Windows Explorer. You'd need a third-party file checksum application or specific ADS detection tools to effectively maintain the integrity of an NTFS partition against unauthorized alternate data streams.
Given how stealthy alternate data streams can be, expert, what's the first thing an investigator should really be concerned about when they suspect ADS, and what's a tool that addresses that directly?
That's a critical question. The first concern should always be that native Windows tools simply won't reveal these hidden streams, making standard checks insufficient. So you absolutely need specialized third-party tools. One excellent example is LADS List Alternate Data Streams, which you can find at www.haysoft.dentep-lads.htm. LADS is designed specifically to list all alternate data streams of an NTFS directory, and crucially, it can even find them for encrypted files.
So LADS can see what Windows Explorer can't.
Exactly. The basic syntax looks like syntax filename.streamgame. You can create an ADS using a command-like type text file visible.txt.hidden.txt, and then view it with more visible.txt.hidden.txt. For investigators, parameters like S to recursively walk through subdirectories and A to show the total bytes of all streams are incredibly useful for comprehensive analysis. It helps shine a light into those dark hidden corners of the file system.
Switching gears a bit, for system maintenance, diagnostics, and of course forensic tasks, having a CD-ROM compact disk read-only memory that's bootable for Windows XP is incredibly invaluable. These tools provide a complete Win32 Windows 32-bit environment, often with network support and a graphical user interface, all running independently of the installed operating system. Two prime examples of such utilities are BART PE Builder and the Ultimate Boot CD-ROM.
Yes, bootable rescue disks.
Exactly. BART PE Builder, that's BART Pre-Installed Environment Builder, helps you create a bootable Windows CD-ROM or DVD from your original Windows XP or Server 2003 installation CDs. It supports various versions, including Windows XP Home and Professional and Windows Server 2003 editions, effectively restoring a complete Win32 environment that can be critical for recovery or initial forensic triage. Then there's the Ultimate Boot CD-ROM. This is a powerhouse that allows Flocky-based diagnostic tools to be executed directly from a CD-ROM on Intel-compatible machines, entirely without needing a separate operating system.
So it packs a ton of utilities onto one CD.
It really does. Its capabilities are extensive. It can modify NTFS volumes, restore deleted files, scan hard drives for viruses, create new NTFS volumes, and even provides network support. The Ultimate Boot CD-ROM includes a vast array of tools. You'll find various CPU tests like CPU burn-in, memory tests such as memtest86, and comprehensive suites of hard disk tools covering installation, diagnostics, and partitioning. It even includes boot managers, file tools, antivirus malware tools, and network tools, plus both DOS and Linux boot disks. The key takeaway for you here isn't to memorize every single test or utility, but rather to understand its basic functions for diagnostics and gaining system access in a forensic context. It's a lifesaver for getting access to a system that won't boot or is otherwise compromised, allowing you to bypass a potentially compromised operating system.
That's a great segue. This raises an important question. With such a wide range of powerful Windows-based forensic tools available, why should an investigator bother learning Linux? What unique advantages does it bring to the table?
Yeah, why add another OS to the mix?
The answer lies in the greater levels of control and unique benefits that Linux provides, often at a very fundamental level. First and foremost, a core benefit of Linux and UniX Uniplexed Information and Computing Service in general is its fundamental philosophy. It treats every device from the hard drive to the monitor as a file.
Everything's a file.
Exactly. This architectural design provides forensic investigators with incredible granularity and control over hardware access. But even more crucially for forensics is its inherent ability to mount drives in read-only mode. This is a game changer because it means you don't necessarily need a separate hardware write blocker to prevent any accidental data alteration on the suspect disk. This is a fundamental requirement for maintaining evidence integrity and ensuring admissibility in court. It's like having a built-in protective shield.
So less risk of accidentally changing evidence just by looking at it.
Precisely. Beyond control, Linux offers immense flexibility. It supports an incredibly broad range of file systems, everything from standard Windows NTFS and FAT2 to Max HFS and various UNIX and specialized formats. This versatility is a huge advantage, as it means you can analyze almost any type of drive you encounter with a single forensic platform. Moreover, the open-source nature of Linux has fostered a vibrant community, resulting in a wealth of highly capable forensic distributions like Air, Sleuth, Auditor, and Helix. Yes, Helix has a Linux version too, which provides sophisticated GUI and command line tools at little to no cost.
So you get powerful tools often for free.
Often, yes. This accessibility and versatility make Linux an incredibly powerful and cost-effective platform for deep forensic analysis, especially for those highly technical investigations.
Okay, let's unpack this concept of everything is a file in the Linux file system because it's truly fundamental to understanding Linux forensics.
It really is key.
In Linux, every hardware device, whether it's a hard drive, a CD-ROM drive, or a USB stick, gets an entry in the file system, usually under the dev directory. So, for example, a standard ID integrated drive electronics hard drive would be listed as dev-hdx, where X is a letter starting with A for the first drive. SATA drives are usually dev-zx.
Right, SATA, S, DB, etc.
And each partition on that drive is then numbered, like devsdal1 for the first partition on the first SATA drive. To really identify the disk structure and see all partitions on a drive, you'd use the command fdisk acohel devsdx. This command lists all the partitions, marks boot partitions, shows their start and end cylinders, the number of blocks they occupy, their file system type, and their unique partition ID. This information is vital for an investigator to map out the physical layout of a suspect drive. Now, let's quickly highlight some of the primary Linux directories, focusing on where an investigator would typically look for evidence. This overview applies to most Linux systems. We've got the root directory, the base of everything, bin essential programs, bootloader files, kernel images, .dev device files, etc. This is critical, right? Configuration files.
Absolutely critical. System settings, user configs, services. Lots of clues there.
Home directories, another prime spot for user data. Lib-shared libraries, MNT, where you typically note temporary file systems like your evidence drive, add-on software about proc that pseudo file system with live process info.
Yes, proc is amazing for live analysis. It's like looking under the hood while the engine's running.
Root the super user's home. Spin system admin commands, TMP temporary files, SRMore software and libraries. And var, this is another big one, especially varlog.
Yeah, varlog is the standard log directory. Authentication logs, system messages, application logs, a gold mine for tracing activity.
And you also have things like varmail for mailboxes, varun for runtime info like PIDs, and varthump for potentially longer-lasting temp files.
That's an excellent focus on the forensically relevant directories. What's fascinating here is that before a file system can be used under Linux, it must be mounted. This is a crucial concept, and it's important to note that Linux can actually write to devices even if they aren't explicitly mounted, so extreme care is always needed. Common locations to place mount points are within the MET directory, and typically only the superuser or root account can create directories there.
So how do you mount safely for forensics?
All right, here's the critical safeguard.
Okay.
When you're working with evidence, you must always mount the drive or image with the O row, that's read-only options. This prevents any accidental changes to the file's last access times or the data itself, which is absolutely fundamental for maintaining evidence integrity. For example, you might use a command like mount rstusseo row, spipsun devht-c2 melt. The O row is often equivalent to AO. Additionally, it's best practice to always use the no exec, no execute, and no dev, no device files options.
Why those?
No exec prevents accidental program execution from the partition you're analyzing, and no dev stops the system from interpreting any character or blocked special devices on the file system. It adds layers of safety. So a typical forensic mount command might look like mount row no exec no devston1 dimi on evidence. This robust read-only capability, coupled with Linux's incredible versatility to support that wide array of file system types we mentioned, Windows FAT, NTFS, Mac HFS, various UNIX formats, makes it an excellent platform. One set of utilities can effectively access data from many different system types.
Here's where it gets really interesting and incredibly practical for forensic analysis. The concept of loop-back devices. These are a game changer because they allow you to mount a file containing an image copy like one you obtain with the deed command as if it were a physical disk or block device.
So you treat the image file itself like a hard drive.
Exactly. Imagine being able to work with a complete disk image as if it were a real, live hard drive without actually writing it back to physical media. The benefits are huge. They're used for creating boot disks, burning CDs, working with encrypted file systems, and, as we're discussing, for highly efficient forensic analysis. To make this even easier, the NASA-enhanced loopback drivers exist. These drivers simplify the process significantly by allowing you to mount a complete disk image as a single loopback device, rather than having to map it partition by partition.
Oh, that saves a lot of hassle.
It really does. It reduces the chance of errors, streamlines the workflow, and makes mounting evidential drives much, much easier. It's a tool that really boosts your efficiency and accuracy when dealing with disk images, allowing you to analyze them non-destructively.
Understanding the Linux boot sequence is crucial for forensic investigators because any modifications to this process can be a strong indicator of system compromise or malicious activity. The sequence begins with the system loading the kernel, which is usually located in the boot directory. The bootloader, commonly ILO Linux Loader or GRUB Grand Unified Bootloader, which is configured in files like eclio.conf or etherebrub.com, specifies the location of the root device, the boot drive, and the kernel version to be loaded.
So ILO or GRB points to the kernel. Then what?
Next, the Linux boot process starts initialization, which is controlled by this BINET program and its configuration file, its syntab. This stage sets up the system's run levels, which describe the system's state. 0 for halt, 6 for reboot, 3 for multi-user text mode, 5 for graphical mode, that kind of thing. Within this initialization, certain startup scripts are of particular interest to us, especially in distributions like Red Hat. These include etcrc.drc.synedit, which handles system initialization, file system mounts, and checks. Then there are the etcrc.drc.local, where setdeceders represents a run level, which calls specific scripts for that run level. And finally, it's setcrc.drc.local, a general-purpose script that administrators often modify to include custom commands needed at boot up for local server customization.
And that rc.local is a prime spot for malware persistence.
It absolutely is, a classic hiding place. After the system is up, you interact with it through a command shell, most commonly bash, the bourne-again shell. But knowing other shells like cache or zsh can sometimes provide clues about user habits or system configuration.
While Linux offers incredible power and control as a forensic tool, it's not without its hurdles. It's important to be aware of these challenges so you can mitigate them in your investigations. What are some of those key challenges, expert?
That's an important point. Despite its strengths, Linux forensics does present a few significant challenges. One is a technical limitation. Linux, or at least some older tools, sometimes had trouble accurately identifying the last sector on hard drives that have an odd number of sectors. This might seem minor, but it could complicate full disk imaging in specific edge cases. Another point of friction for many new users is that the majority of Linux forensic tools are primarily command line based. While incredibly powerful, this does increase the learning curve for those unfamiliar with text-based interfaces. It means you'll need to invest time in mastering commands rather than just clicking icons.
Okay, steep learning curve for the command line. What else?
Perhaps one of the most significant challenges, and one that requires constant vigilance, is the persistence of write access. Even though it's possible and forensically critical to mount an image as a read-only file system using options like do-row, it is still possible to write directly to the physical drive device, like devsda, if you have the appropriate permissions in Linux.
Wait, even if the mount is read-only, you could still write to the raw device.
Yes, if you're not careful or if you have root privileges. This means that while the mounted file system itself might be read-only, if an investigator is careless or makes a mistake, they could directly alter the physical evidence by accessing devsda directly. Forensic care is paramount here. You need to be mindful of using the device node directly versus the mounted file system. Finally, while all software can have bugs, Linux is sometimes perceived as being riskier in some legal circles, perhaps due to unfamiliarity. This could potentially affect the credibility of your findings if not handled with meticulous documentation and established procedures.
Okay, so that's a clear-eyed view of the challenges. But despite them, Linux truly is a forensic powerhouse, and it includes several simple yet incredibly powerful utilities that form your command line arsenal for imaging and basic analysis of suspect disks and drives. What are some of the essentials we should know?
Absolutely. The foundational tool here is DD Data Duplicator, It's a command used to copy from an input file or device to an output file or device, often referred to as bit streaming, for creating exact copies. An advanced variant, DCCSLDD, takes DDD a step further by showing progress during the imaging process, providing hashing on the fly, and other forensic enhancements. It's a huge quality of life improvement, especially for large drives.
DCSLDD for progress and hashing. Good tip.
To understand the physical layout of a disk, SDisk or SDisk are your go-to commands. For searching text within files, grep global regular expression print is indispensable. It allows you to search files for instances of an expression or pattern using powerful regular expressions. As we discussed, the loopback device is a crucial feature that allows you to mount a file containing an image as if it were a physical disk without needing to rewrite the image to an actual drive. Saves time and media. For ensuring data integrity, MD5 and SHA-SUM are essential for creating and verifying MD5 or SHA hashes of files or entire devices.
Hash early, hash often.
You got it. To determine a file's true nature, regardless of its name or extension, the file command reads file header information. Magic numbers, basically. For low-level examination, XXD is a command line hex dump tool, while gex and kexedit provide graphical hex editors for GNOME and KDE desktop environments, respectively. These tools, while simple, form the backbone of many Linux forensic investigations, giving you incredible control at the raw data level.
Okay, let's unpack this with a mini case study. This is how you'd put these powerful Linux command line tools into action for imaging a system step by step. Imagine you've just seized a suspect machine.
All right, let's walk through it.
Step 1. Document everything. This is crucial for maintaining a solid chain of custody. You'll also begin by creating directories for your forensic activities, for example, mkdir evidence to store your findings, and mkdir mn case 1 as a mount point for analysis. Step 2. Determine the disk structure. You'd use fdisk-l devsdx for that, replacing devd with your actual target drive, say devsdb. This gives you a map of the partitions. Step 3. Image the disk. You'd use devs-sdd for its forensic features. devsdb of evidenceimage.dd hash MD5 a SHA-1 hashlog evidenceimage.hash's status on. This images devsdb to image.dd, calculates MD5 and SHA-1 hashes on the fly, logs them, and shows progress.
That DCSFVD command is much better for forensics than plain DD.
Definitely. Immediately after, you must change the image permissions to read only using chmod 440 evidenceimage.dd to allow read access for the owner and group, or chmod 400 if it's just for you. This is a critical step for evidence integrity. Step 4. Verify data integrity. You already have the hashes logged by DCFLTD, but you can re-verify later using MD5 sum nashc evidenceimage.hashes or shrchutsum mashsameo evidenceimage.hashes pointing to the correct hash line. Step 5. Mount the working copy. Ideally, you'd use the loopback interface for your image file to avoid touching the original. Mount nasharo noexec nodev loop evidenceimage.db mnt case 1. This mounts the image read-only, preventing any accidental execution or device issues from the suspect image.
Loopback mounting is key for image analysis.
Step 6. View disk contents and search for strings. Now you can explore ls-arl2 mnt case 1 evidencefiles.list will list all files, including hidden ones, recursively by time, sending the output to a file for later review. You can then grep I keyword evidencefiles.list to search for suspicious keywords in file names or paths. Step 7. Analyze files further. For deeper inspections, strings mn case 1 path to suspect file will extract printable characters from a binary file. cat more or less can display text file contents. For systematic keyword searches across the entire raw image, create a keyword list file with 1 keyword per line, and then run grep-abf keyword list evidenceimage.dd evidence search results.txt. This command finds matches across the entire disk image, saving the output.
AFI treats binary as text, ignores case, -b shows the offset, and AFF uses the keyword file. Powerful combination.
Step 8. Display results and analyze at offset. You can then cat evidence search results.txt to see your keyword hits with their offsets. And for pinpoint binary analysis, xxd xxs offset evidenceimage.dd lease lets you view the hex dump starting at a specific offset found by grep. This structured approach ensures a thorough and forensically sound investigation using just the command line.
If we connect this to the bigger picture, while those individual Linux commands are powerful, for a comprehensive and organized approach to file and volume system forensic analysis on UNIX-like systems, the Sleuth Kit, TSK, is indispensable. TSK is a collection of command line tools originally based on the Coroner's Toolkit, and it truly shines because it's not intrusive. It doesn't rely on the operating system to process file systems, which means it can reveal deleted and hidden content that the live OS might obscure.
So it bypasses the OS's view of the file system.
Exactly. Its graphical front end, the autopsy browser, then takes these powerful command line tools and wraps them in an intuitive interface. The key benefits are numerous. TSK and Autopsy are open source, running on platforms like Linux, OS X, FreeBSD, OpenBSD, and Solaris. They can analyze a wide range of file systems, including NTFS, FAT, X2123, UFS12, and various volume system types like DOS partitions, BSD slices, Mac partitions, Sun slices, and GPT GUID partition table disks. The volume system tools within TSK are particularly useful for examining disk layouts, helping you identify partition locations and even extract them for further analysis. Autopsy Browser then adds critical features like case management, image integrity validation, sophisticated keyword searching, and other automated operations, making it a complete forensic hub.
To give you a better sense of the Sleuthkit's power, let's break down its tools by the general layers of the file system they operate on, focusing on their primary function for an investigator.
Good idea. TSK has tools for each layer.
At the file system layer, dealing with overall structure, you have STAT. This gives you the blueprint file system details, stats, layout, sizes, labels. Moving up to the file name layer, processing names and directories, you'll find SLS and FDUND. FSLs is crucial. It lists allocated and deleted file names in a directory. Really important for seeing what was there. FDUND finds names pointing to specific metadata.
That FLE showing deleted file names is huge.
Then the metadata layer details about a file like directory entries, MFT, master file table entries, or inodes, index nodes. Here, ISStat is key. It displays stats about a metadata structure, timestamps, size, data block locations. ICAT extracts the actual data based on this metadata address. IS lists metadata structures. Below that, the data unit layer where content is stored. Clusters, blocks, DLs lists data unit details, and critically can extract unallocated space. DCAT extracts the contents of a specific data unit. DTAT shows stats about a data unit.
Extracting unallocated space with DLs is vital for finding deleted file content.
For file systems with journaling, like XT34 and NTFS, there's the file system journal tools. JLS lists entries in the journal, key for recovering recent changes or deleted metadata. JCAT displays specific journal block contents. TSK also includes media management tools like MLLs, which displays the disk layout partitions, unallocated spaces, types, lengths. Great for understanding the raw disk structure.
MLOs helps you see the partitions before you even analyze them.
And image file tools like ImgStat show image format details, while ImgScat outputs the raw image contents. Plus, disk tools, Linux only, like DiskStat and DisksReset, can detect and temporarily remove a host-protected area, or HPA, on ATA disks. Finally, the miscellaneous tools include MacTime, which creates a timeline of file activity using modified access change times from spales and PSDES output. MSHFIND looks up hashes in databases like NIST NSRL or hashkeeper.sorter, sorts files by type and checks extensions. And SigFind searches for binary values at specific offsets, useful for data structure recovery. It's a really comprehensive suite.
That's a fantastic overview of TSK's capabilities. This raises an important question. How do you actually use this powerful toolkit in a graphical environment? Let's walk through a step-by-step approach to running Autopsy, its graphical front end.
Okay, let's see Autopsy in action.
Step 1. You'll start by booting your computer using a Helix bootable CD-ROM or similar Linux forensic distribution. You'll get to the Linux desktop like in Figure 6.10 of your study guide. Step 2. Once booted, you'll navigate to launch the Autopsy Forensic Browser, maybe through a menu like Forensics Autopsy. Its main screen will then appear, similar to Figure 6.1m. It usually starts a web server and gives you a URL to connect to in your browser. Step 3. To begin your investigation, you'll click New Case, as highlighted in Figure 6.1. Step 4. You'll then enter your case, details the case name, a description, investigator name, and click New Case again, as seen in Figure 6.400. Step 5. Pay close attention to the Creating Case screen, depicted in Figure 6.14. It's vital to note where the evidence directory is located, as this is where all your case-related files will be stored. Choose this location carefully.
Keep everything organized.
Exactly. Step 6. Next, you'll click Add Host and fill in the form that appears, providing details like the host name, a description, its time zone, and any clock skew, as shown in Figure 6.15. Clock skew adjustment is important for accurate timelines. Step 7. Similar to the case directory, make sure you note where the host-specific data is located, as you'll be presented with this information much like Figure 6.16. Step 8. Now it's time to add the disk image you want to analyze. You'll press the Add Image button. Autopsy expects that you've already captured an image of the disk using DD or DCS LTD, so you'd point it to a file like home.chfi.amg.
So you add the image file you created earlier.
Correct. Step 9. From the Add a New Image screen, you'll select the exact location of the image file, specify the import method like copy or link, and the image type, disk or partition, as illustrated in figures 6.17 and 6.18. You'll also calculate the hash here to verify integrity. Step 10. Once the image is added and analyzed, which can take time, you can go back to the case gallery to see all your available options for this case, similar to figure 6.10. Step 11. From there, you're ready to continue to explore Autopsy's many features, file analysis, keyword search, timeline, and begin the actual analysis of your image using the various options shown in figure 6.2. This step-by-step process helps you organize your investigation and leverage TSK's power effectively through a user-friendly interface.
Autopsy truly acts as a comprehensive forensic hub, providing that graphical front end for the sleuth kit and integrating various other tools. It offers a full suite of analysis, search, and case management capabilities. It's important to distinguish between the two primary modes of analysis it supports: dead analysis and live analysis.
Right, the context matters.
Dead analysis occurs when you're examining data from a suspect system using a dedicated analysis system in a trusted environment, typically in a forensic lab. In this scenario, Autopsy and TSK run on your secure workstation, and they support RAW, Expert Witness, EO1, and AFF file formats for disk images. In contrast, live analysis, using tools perhaps launched from Autopsy on a live system, the less common for Autopsy itself, more for initial triage tools, happens when you're analyzing the suspect system while it's still running, often from a CD or USB drive in a non-trusted environment. This method is frequently used during the initial incident response phase to confirm an incident. Following confirmation, the system is usually acquired, and a more thorough dead analysis is performed offline. Autopsy offers a robust suite of evidence search functionalities. For file listing, you can analyze files and directories, including deleted files and those with Unicode-based names.
Seeing deleted files easily is a huge plus.
Absolutely. File content can be viewed in raw, hexadecimal, or extracted as ASCII strings, with Autopsy sanitizing data to prevent damage to your local analysis system. It also leverages hash databases like the NIST NSRL and custom databases you create, known good bad, to quickly identify known files and filter out noise. For further classification, file type sorting arranges files based on their internal signatures, magic numbers, extracts graphic images and thumbnails, and compares extensions to true file types to detect hidden files, like an exe renamed to JPG.
That extension mismatch check is crucial.
It really is. A timeline of file activity can be generated using modified access change MA times for both allocated and unallocated files, which helps pinpoint activity around the time of an incident. Its powerful keyword search function supports ASCII strings and GRP regular expressions across the full image or just unallocated space, with index files for faster searches. And metadata analysis allows you to view the details of any metadata structure, like an inode or MFT entry, which is invaluable for recovering deleted content and identifying the full path of allocated structures.
So you can really dig into the file system structure itself.
Exactly. And beyond analysis, Autopsy provides excellent case management functions. The event sequencer lets you add time-based events from file activity or external logs, sorting them to easily determine the sequence of an incident. Notes can be saved per host and investigator, linking directly to the evidence stored in plain text. Image integrity is automatically maintained by generating and checking MD5 SHA1 values. Reports can be created in ASCII or HTML, ensuring consistent datasheets. And robust logging creates audit logs of case actions and sleuthkit commands executed, providing a complete auditable trail.
Beyond Autopsy of the Sleuth Kit, the Linux forensics landscape offers a rich ecosystem of specialized tools. Let's touch on a few more key players that you might encounter, highlighting their unique contributions. Smart for Linux by ASP Data is a commercial GUI tool. It really excels in those knock-and-talk inquiries, on-site previews, and post-mortem analysis. Its strength lies in its intuitive interface displaying connected storage, partitions, drive info. It's great for rapid assessment.
So good for a quick look on site.
Exactly. Then there's the Penguin Sleuth Bootable CD, a fantastic adaptation of the Knoppix Linux Live CD, packed with forensic and security tools. Beyond a standard Linux desktop, its forensic tools include TSK, Autopsy, DCFLDD, Foremost for data carving, and even RegiViewer for Windows registry analysis, plus security tools like Smart and John the Ripper. It offers a comprehensive, ready-to-go, self-contained forensic environment. Another interesting development is the Farmer's Boot CD, FBCD. This embodies an emerging trend, previewing a system before committing to a full image.
Save time and disk space if there's nothing there.
Precisely. In today's world of massive hard drives, this can save immense amounts of time and storage. The FBCD's core goal is to securely and promptly sample systems, hard drives, USBs, camera media to quickly identify evidence and help decide whether to image. It offers a unified GUI for previewing, can automatically mount file systems forensically, and provides specific previews for Windows data, recycle bin, event logs, browser history, and Linux data, logs, recently used files. It's all about efficiency and making informed decisions quickly.
Okay, let's unpack this and bring it all together. We've covered a lot of ground. What stands out for you as the most critical takeaways from this deep dive into Windows and Linux forensics?
If we connect this to the bigger picture, I think the absolute most critical takeaway is understanding the complementary strengths of Windows and Linux in forensics. You really need both. Windows excels at capturing that volatile data from live systems, the stuff that disappears when you pull the plug. Linux, on the other hand, offers just unparalleled control at the physical layer, that inherent read-only mounting capability, and a vast array of powerful, often open-source analytical tools that provide incredible depth.
So use Windows for live capture, Linux for deep analysis, maybe?
That's a good starting point, yeah. Another key point is volatile data collection. Never, ever underestimate its importance. Always prioritize collecting volatile data registers, cache, memory processes, network connections first, meticulously following guidelines like RFC 3210E7. It's the smoke from the fire, critical for understanding the immediate state, and it is incredibly time-sensitive. Don't skip it. For Windows environments, you need to be proficient with essential tools. This includes comprehensive suites like Helix and FTK Imager, command line powerhouses such as the CStool suite, particularly the Pslist, Fport, Psloggedon, and specialized utilities like RegScanner and Internet Trace Viewers. Crucially, understanding concepts like file slack and alternate data streams, ADS, is absolutely vital for uncovering hidden data.
You have to know where attackers hide things.
Exactly. On the Linux side, your toolkit should include foundational tools like DD, or preferably DCLTD for bitstream imaging, grep for powerful text searching, and especially the Sleuth Kit, TSK, with its autopsy browser GUI for in-depth analysis of file systems, metadata, and data units. And don't forget the concept of loopback devices. They significantly enhance the efficiency of image analysis. And finally, regardless of whether you're working on a Windows or Linux system, the principles of integrity and documentation are paramount. This means meticulously maintaining the integrity of your evidence through cryptographic hashing, like MD5 or SHA-1, and documenting every single step you take, from initial collection to final analysis. This fastidious adherence to the chain of custody is non-negotiable for ensuring evidence admissibility in court.
So what does this all mean for you as an aspiring or practicing digital forensic investigator? It means becoming truly effective requires fluency in both these major operating systems. It's about having a flexible mindset, adapting your approach based on the environment, and building a diverse toolkit that leverages the unique strengths of both Windows and Linux. Always remember to minimize any alteration to the suspect system and meticulously document every action you take. This dual expertise isn't just an advantage, it's an absolute necessity to conduct a comprehensive and credible forensic investigation in today's mixed digital landscape. What's fascinating here is that every digital investigation is ultimately a puzzle, and sometimes the most important piece is hidden in plain sight, or maybe in a place you didn't even know existed until you understood the nuances of the operating system and the powerful tools at your disposal.
This raises an important question for you, the listener. As you continue your journey in digital forensics, consider how the fundamental principles of evidence preservation and analysis remain constant, even as the underlying technologies and the operating systems themselves evolve rapidly. How will you adapt your toolkit and your investigative mindset to the future operating systems and the new, yet-to-be-discovered hidden data locations they will undoubtedly introduce? The landscape is always changing, so continuous learning is key.
That's a great thought to leave you with. We've unpacked a huge amount of information today, from the volatile secrets of Windows to the deep control offered by Linux, and explored an incredible array of tools for both. Join us next time as we continue our deep dive into the EC Council CHFI curriculum. Until then, keep digging for those digital truths.